Welcome to this video. My name is Sumit Bhushan, and in this video we are going to discuss about instantaneous velocity. So what is instantaneous velocity? So as the name suggests, it is the velocity of a particle. It is the velocity of a particle at any given instant of time. Fine. Okay. So now the question arises. Why do we need it? Why do we need instantaneous velocity when we are having other parameters to describe the question about how fast a particle is moving? We are already having average velocity and average speed. Then why do we need these parameters answer that how fast an object or particle is moving? Then why do we need another physical parameter like instantaneous velocity which answers how fast? So generally when we ask the question how fast a particle is moving, then generally broadly we mean that how fast that particle is moving at a given instant of time. So for example, let us say, so we are having our discussion in the context of one directional motion. Okay, so this is from one directional motion point of view. So let us suppose that any particle, or let us say there is a car that is moving along the x-axis. So this one is the x-axis. So it is moving along the x-axis so that its position at t1 is x1 and its position at t2 is x2. Then we say that the average velocity v average, its magnitude is equal to x2 minus x1 upon t2 minus t1. So you see this average velocity gives us the value of the rate at which the car is moving for defined period of time. So for any period of time. So here the period of time is t2 minus t1. But when we want to know that how fast this car is moving at t1 precisely, so then this average velocity is not going to answer that question. So for that we need a concept like instantaneous velocity. So I hope that point is clear to all of you. Okay, so that is one thing. Again, so we use the term velocity rather than instantaneous velocity whenever we want to discuss about instantaneous velocity. So from this point on we will be using the term velocity only, and we will mean instantaneous velocity unless otherwise specified. Okay, so now let us define it mathematically. Let us try to, or rather before defining it mathematically, let us try to have an idea what does it physically mean to describe a quantity like instantaneous velocity. So it is obtained, so velocity is obtained from the average velocity itself, by letting the time period approach 0. So that is what we mean. So we just said that the instantaneous velocity is demanded in a situation when we want to know the rate at which any object or particle is moving at any given point of time, given instant of time. No, we don't want its speed for a given interval. No, for that we are already having average velocity, right? So when we say instantaneous velocity or velocity, we need to find how fast that object is moving at any given instant of time, like in this case at t1 or t2 maybe, or any other given instant of time. So now we have said here in this statement that velocity is obtained from the average velocity by letting the time period approach 0. That means if in this case we go on reducing this time period, okay, so that it is more and more closer to t1, then maybe in the limit that this time period is 0, we obtain the velocity. So mathematically, so before going in mathematics, let us try to understand this thing pictorially. So let us again go back to the example of a car moving on a straight line. Let us say it is moving on x-axis. So like previously, this car is having this kind of position. So at, let us say this one is t1 equal to t, or rather t itself. So t equal to 1 second, and this is at t equal to 2 seconds. Its position at t is equal to 1 second is x1, let us say, and at x2, at t2 is x2. So average velocity here the average velocity, what will it be? x2 minus x1 over 2 minus 1, right? Over 2 minus 1 meter per second, of course. Now what will happen if we shrink this time period, so that we ask the question that from here the next question is, what is the average velocity in this time period when t, the initial time is still the 1 second, but now we want to ask that what is the average velocity between t is equal to 1 second and let us say t is equal to 1.1 second. Okay, so average velocity is x, so this one here still it is x1 and x 1.1 second. Okay, so x 1.1 minus x 1 over 1.1 minus 1. So this, you see, in denominator it is 0.1 second. So compared to this situation, in this situation the car has traveled lesser distance in comparison to this situation. Okay, because the time elapsed in between these two time, I mean the instants of time is lesser than the time elapsed in this case. It is here the time passed is 1 second, here the time passed is only 1 second. So the average velocity is rather closer to the velocity that the object was having at t is equal to 1 second. Now let us reduce the time further by 1 order maybe. Okay, so here again it is t is equal to 1 second and here t is 1.01 second. So this one is position is x1 and this position is 1.01. Okay, so now in this case let me divide these three cases by these linings. In this case the average velocity is, what is it, x 1.01 minus x1 over 1.01 minus 1. So in this case the average velocity is still closer to the velocity that the object was having at t is equal to 1 second. Okay, so we see that as we go on shrinking the size of the time period, then the average velocity approaches the velocity, the instantaneous velocity at the beginning of the time period. So if you have studied mathematics, the calculus part, then you might be knowing that this situation is best described by something called the limit. So we see the definition of average velocity, mathematical definition is, what is it? X. So delta x over delta t. So here in this situation, what we have done, we have shrunk the size of delta t so that it approaches 0. So this is the instantaneous velocity. So you see this one is equal to dx by dt. So you see the average velocity was the displacement over time, but the instantaneous velocity is its limit when delta t approaches 0. So it is the derivative of x, where x denotes the particle's position. So what does this expression mean? What are the special meanings of this expression? So this is for instantaneous velocity or just velocity. Fine. So now we have seen that velocity v is the rate, it is the rate at which position x is changing with respect to time t at any given instant of time. Okay, we will see that, you see, any derivative, in the case of any derivative, it is also the slope of the curve at any given instant. So if we have the slope, we have the curve of position versus time, where on y-axis we are plotting position here, and on x-axis we are plotting time. Okay, so this average, so this instantaneous, for example, if you want to know the velocity at this time, let us say it is t1 and the position is x1, so we want to know the velocity at this instant. So according to this mathematical expression, the velocity will be the slope of this curve at this point of time. So we know that the slope is tangent here, but it is given by the derivative of x. Okay, fine. Moreover, since v has been derived from, v means instantaneous velocity, has been derived from the average velocity, which was a vector quantity. That's why v itself is also a vector quantity. So instantaneous velocity is a vector quantity. So its complete explanation should involve both its magnitude as well as its direction. Right. So another thing is, another concept, so like in the case of average velocity, there was a parameter average speed. Similarly, in the case of instantaneous velocity, we will be having instantaneous speed or simply speed. So you see why is this quantity needed? Because in the speedometers, you see speedometers on your vehicles, they give you this quantity, speed only. So this is a scalar quantity. This is a scalar quantity, and that's why it is having magnitude only. It is having magnitude only and no direction. There is no direction associated with the average instantaneous speed or speed simply. Okay, so it is the speed is the magnitude. What is it? It is the magnitude of velocity, right? So be careful that since it is just the magnitude, that means, for example, if the instantaneous velocity or the velocity is, let us say, plus 2 meters per second or minus 2 meters per second, in both of these cases the speed will be only 2 meters per second. There is no directionality involved with the speed. That's why we have said that the speedometers on your cars or bikes, they tell you about the speed because there is no direction involved there. Okay, so they don't the speedometers do not tell about the velocity. Okay, so now we have discussed all of these things. Let us try to solve one example here quickly. So the question here is find the magnitude of the velocity. We only want the magnitude of a particle for which the position has been given in the following situations. You see, position has been given here. There are three situations, A, B and C, and it has, so position is x and it is a function of t. Okay, so it has been said here that in all of the above situations x is in meters and t is in seconds. Fine, so it is given. So we want to find the magnitude of the velocity. So velocity means instantaneous velocity, and just now we have defined that velocity is equal to d by dt of x. So in A we are having xt is equal to 2t square plus 1. So xt is equal to 2t square plus 1. Therefore the velocity is d by dt of 2t square plus 1. So from mathematics you know that it is 4t. Okay, so this velocity is 4t, the magnitude I am saying. So for example, at t is equal to let us say 2 seconds, it will be velocity at 2 seconds will be 4 into 2 is equal to 8 meters per second. Right, now B, what was B? Let us see. Xt is equal to minus 3t minus 5. What is it? It is given that xt is equal to minus 3t minus 5. Again, velocity is d by dt of xt is equal to d by dt of minus 3t minus 5. So it is equal to minus 3. That means it is a constant quantity. Okay, velocity is minus 3. Of course, it is meter per second. Now the last one was xt is equal to minus 2. So the position itself is constant. You see, it is just minus 2. It is not given. So there is no time involved here. So that means the velocity, since it is d by dt of xt, and you know that the derivative of any constant function is 0. So therefore, in this case, the velocity is 0. So in the cases B and